Let's start and just introduce again Dmitry. So Dmitry is part of Yandex Toloka team, and he has extensive background in NLP, but also in crowdsourcing and application of crowdsourcing for NLP. And yeah, I think it's really a great opportunity to learn from him about this technology, as for many natural language processing problems, the success or failure really depends on the quality of the data and data set, much more than on the machine learning algorithm or model which is used. And yeah, let's try to understand today what one has to do to get some really nice data for some custom problem to be able to get good results for your task. Okay, Dmitry, so thanks for...
Thank you very much for the introduction. Today I will tell you something about the overview of the whole crowdsourcing activities that take place on the internet. So crowdsourcing is a very broad term, and it is not all about micro tasks and stuff that you might have seen before at maybe Yandex Talaka or Mechanical Turk, etc. But I think crowdsourcing is a very large concept, and in this lecture I will show you some examples of this concept, and I will show you how to reason about it and how to provide better quality data, better instructions, and better understanding of how it works in particular. So I work at Yandex at the data analysis and research group. I was working as a postdoc at the University of Mannheim before, if you haven't seen my lecture past week. So at Talca, I'm responsible for crowd activity analysis, product metrics, and suspected fraud investigation. And also I'm making an organization of crowdsourcing tutorials all over the world that we organize at various scientific conferences. And I'm really happy to tell you something that I knew about crowdsourcing before I joined Yandex, and I really hope it will be useful for you. My talk today will be composed of 6 parts, and I think the most contentful parts are second, third, and fourth. I think after the second part we'll take a break, and maybe third part will also take a break. And before I start, I'm just curious about how many people here have used crowdsourcing before. Well, I see one raised hand, but maybe more. I don't see any raised hands. That's
Maybe
perfect.
you can type plus in the chat. I know some of you do.
Yeah, I see at least one plus, which means that you'll get something to learn. Okay, one more. Cool. Okay, so not so much, which is great because you'll learn something today. Let me introduce the concept. So let's focus on the natural language processing first. And as you know, probably natural language processing, like any other machine learning application, requires some data sets. And these data sets are usually annotated. They have to contain some labels, and you use these labels to train your classifier or some regression model, whatever. And you need those labels to predict new labels. So you're doing prediction. And these data sets are also known as language resources. And there are some large conferences on language resource creation and evaluation. And there are some people that are focused on creating high quality language resources. Usually they are expert linguists. They know the language very well, but the problem is this approach does not scale for, really large data sets. You need something else, and this something else is crowdsourcing. This approach allows you to gather some data, and this data has been found to be of very high quality, and you obtain this data from non-expert annotators who are trained in some sense by you to perform this task. And crowdsourcing is a very efficient approach for large-scale knowledge acquisition, data annotation, and so on. We will focus on crowdsourcing for NLP, and we will learn how it works and how to make it, how to cook it well, basically. So, and my core idea is, since you are proposing some tasks to the people, you need to trust them because they are volunteers who are trying to help you, but you need to verify the quality of their results. And this is how we can build and evaluate NLP datasets using crowdsourcing. Before we continue, let's think about, do we really need it? I would argue that yes, we need crowdsourcing to build language resources, and we need language resources for NLP because you need supervised data to train your classifiers. You need some evaluation data sets to learn whether your classifier or other model is good or not. You need some, if you propose a new data set, you need some quality assessment and so on. Of course, today's machine learning methods are largely built on some unsupervised data like raw text corpora and so on. And you can somehow reuse or merge or join the existing data sets, but crowdsourcing allows you to evaluate the quality. And this is a great feature of crowdsourcing. And of course, the question is, how can we produce language resources for NLP? If we need some data set, we can either use some unsupervised learning approach. For instance, you can bootstrap some sense inventory, you can bootstrap some lexical resource using clustering or clustering in particular. You can invite some expert annotators, which are called assessors, to produce some labels, or you can opt into crowdsourcing. And in this case, you will need some expertise to run it. How it's basically used for NLP tasks. I would select three particular kinds of applications and let me show them. And first, crowdsourcing is built is used for language resource construction, in which you gather some data from people and you use this data to some, to some application. You can provide annotation of your language resources. So you suppose you have some collection of texts called a corpus, and you want to provide part of speech labels for each word. So it's called annotation task. You don't construct a new resource, you annotate the existing. And evaluation. Suppose you have a machine learning model and you want to know how well does it predict something. And in order to make evaluation of those predictions, you can use crowdsourcing for this. And one of the earliest successful examples of crowdsourcing was search relevance evaluation. So you have some query, you have a document, and you need to grade the quality of the prediction. If you have any questions, you can ask me using voice because I would like to look at the chat at the end of the lecture. So if you have questions so far, please ask me. Okay, cool. Let me continue. And before we start thinking about some technical concepts, let's do some more, high-level description of the field. So crowdsourcing is some kind of activity in which there are people who are performing some task. This task is proposed by the requester, and usually the requester uses some platform to deliver this task and to interact with the crowd of performers. And this allows you to get these labels. Depending on your task, there are some genres of crowdsourcing, and these genres tells you how can you design your task. In particular, you have some wisdom of the crowds genre, like Wikipedia or open source software, where people voluntarily go to some website and contribute to some articles or maybe source code files and so on to do something together. There are microtasks, which are usually some paid activities which are performed on other kinds of platforms. And there are some games, which are a funny way to spend your time, but they are usually not paid. So, wisdom of the crowds.
Sorry, I have a question about these games. So you suggest that usually it's not a very mainstream or robust way to get some reasonable data collections, or it's rather like depending on the luck. Like if the game gets popular, we can get actually some really nice data sets, or it's well. in principle possible, but in reality, it's rather unlikely that we have to use it as a technology.
I would say that game development is hard, and if you want to develop a game, you need to invest heavily in the development, and it takes a lot of effort to do. What the coolest part here is you can attract people who will spend their time with purpose, and at the same time they will have fun. But the problem is it takes so much time to develop, it takes so much time to maintain because it's a video game and a multiplayer video game that sometimes it's simpler to use another kind of maybe crowdsourcing platform to gather responses. However, when it comes to the quality is generally good because people who are playing your game really want to win, not to lose. And if you design your game such that people who are doing good things, providing good data, are winning the game, you can get high quality responses. And in the end of lecture, I have some examples about that.
Okay, great. So that was my question, like about some example, successful examples. I was really curious about
Yeah,
what kind of, yeah.
just don't quit and you'll see it. Thank you. And the first kind of crowdsourcing that is probably used by you every day is called wisdom of the crowds. This is the kind of crowdsourcing when you maintain some website in which people can register and just start contributing. And the obvious example is, of course, Wikipedia, in which there are some volunteers who are performing some edits driven by altruism. They generate content, they do some edits, they discuss some phrases and so on. And the requester is usually a non-commercial organization. So Wikimedia Foundation is a non-commercial organization that don't have profits. And you can see sometimes on Wikipedia, some people are trying to request some donations, which is perfectly fine, but it's not the only example. For example, there is a service called Genius. Genius is a service which explains the lyrics of rap songs. Sometimes there are some references which are not obvious, and people are annotating text by providing some explanations. And this service is operated by a commercial entity. There are also much more examples, but the core idea is you have some platform that people enjoy, and some volunteers contribute to this platform. As the result, people get more content of better quality. The coolest part of Wikipedia and so on is that Wikipedia is a proven text corpus which has very successful applications for a lot of NLP tasks and knowledge engineering tasks as well. For example, data from Wikipedia is parsed and somehow structured to provide such knowledge bases as DBpedia, BabelNet, and so on. And for examples, if you have attended my previous lecture about graph clustering, I was using Wiktionary data to organize these experiments with sense induction, frame induction, and so on. So these resources are free. They are available under permissive licenses, and you can use this content very easily. It's an example of very good contribution to the society as well. If you haven't seen Wikipedia before, which is probably unlikely, here's the example of Wikipedia. This page is all about graph theory. There's some description, there's some figure, there's some reference, and so on. And this content can be parsed, can be reused, can be utilized for your NLP application. There's another example called Wiktionary. It's a Wikipedia-style lexical resource in which some words are provided with some examples, etymological references, some sense descriptions, and so on. Here's the example for the kitten. And one more example. I'm sorry for providing you the original text without some translation. Yeah, I'm sorry if you don't speak Russian, but the core idea is this is a language resource built using crowdsourcing in a very similar form. You have some data set, and this data set is provided on the left-hand side. You have some words, and you have some usage examples and sometimes the definitions. And your goal is to group these words into sets of synonyms by putting some words from the left-hand side to the right-hand side by clustering them manually. This is an example of another crowdsourcing initiative. let me discuss the quality issues in the wisdom of the crowd genre. Of course, the major problem of Wikipedia, for example, is when there is a page about some person, and this person gets offended by what's written there, and this person comes to serve justice, so comes to maintain the right perception of the world, and so on. So it could be biased. And there are some spam, there are some advertisements put there are some other weird things that really uh, don't improve the content. And the primary issue of Wikipedia quality is unwanted contributions. And the core idea is the rejection of unwanted contributions is the Wikipedia's primary quality control approach. So they are trying to allow you to contribute something, but in order to do so, they provide some filtering approach to disallow the malicious contributors to provide some responses. Uh, how do they do that? They have basically two approaches. First, they are trying to focus the community effort to look at the pages that require some attention, and also they perform edit patroning. If you use Wikipedia just as a reader, you will not notice that. But if you look at the edit histories, if you look at the discussions, if you look at something else, you will find that Wikipedia is heavily optimized by bots. And let me show you some examples. But before we proceed, let's think about this. Uh, a few slides ago, you have seen a screenshot of Wikipedia. Here it is. My question is the Wikipedia page in the screenshot good? Do you have any answers?
Is the page overall good or the content or?
Let me rephrase the question then. Suppose you see this page, right?
Yeah.
What do how do you think, is it of high quality or not?
Yeah, as a user, I would say it's of reasoned quality.
Yeah, for me too. Exactly. I agree with you, and I hope everybody is agree with me. But my another question is why? Why do you think so?
Well, I think one of the reasons because there is some content which is also cross-referenced to other parts and illustrated and structured. So low quality pages are usually just don't contain almost any information, don't contain disambiguation. Well, they just
Yeah.
don't
But
contain any Wikipedia layout information. And,
exactly, and that's the core point. Let me show you. The page contains text, contains images, links, sections, and so on. So someone has put some effort to make this page looking good. And eventually these features are good indicators of high quality or featured article. Featured articles are the articles that are shown on the main page as like good articles that could enjoy some attention for you as a reader. And the cool idea here is, since we can use these content-based features, we can automate quality assessment using supervised learning. Just predict the quality class of the article using these features. And the cool part, and maybe amusing part of it, is what if you consider every article that has at least 2,000 words as good? And the answer is the binary classification in this case, so good or bad, will be like 97%. The accuracy will be 97% or 96, which is a lot. So if you simply take these features and you say every article that has at least 2,000 words is good, others are not, will be already a significant indicator of a high quality article, because not every spammer, not every malicious performer, not every malicious contributor will take some time to write something. Of course, this feature can be easily abused. You can just copy paste stuff. And of course, this is not the only feature used for classification. Of course, it's usually composed with other features. And as examples, you can look at page edits. So you just compute the number of times this page was edited, how much discussions there was how large is it? You can see the concentrations of editors. In Wikipedia, there are some regular people who can write some pages. There are some editors and moderators and so on. There's a huge hierarchy of people. You can see the concentrations of those who have some moderator rights. You can evaluate readability scores, because spammers who just put some links will not care too much about readability. And what is really funny here is same principles about the content are applicable to other collaborative projects such as Wiktionary and so on. And right now on Wikipedia, there is a system called ORES. In the past, it was called Objective Revision Evaluation System. Right now, it's just the proper noun ORES. It's presented in 2020, so this year, but it was developed before. And this system uses some machine learning techniques called gradient boosting just to predict the damaging page revisions. So suppose you have a page and some people are proposing some edits, and the system provides the moderators with the scores, and the low scores just get some attention, and people are trying to reject these edits. So if the edit is potentially damaging, it gets rejected, sometimes even without human interruption. But if it's reviewed, the system learns based on the new information and tries to predict it better next time. So this is the core idea of Wikipedia. You try to squeeze the most useful edits, and you try to discourage bad edits. So it works as a filter. Here is how it works. If you look at some page histories, you'll see that there are some labels like R on the left-hand side, and these edits are marked as bad. And there are some legend, and this legend explains that these edits are probably bad, and you don't have to accept them. This is not the only initiative. This is not the only bot that works on Wikipedia. And there are a myriad of bots that are trying to maintain and simplify some human tasks to reduce the human effort needed to maintain a good quality of the resource. And there are some other bot called ClickBot-NG, which prevents vandalism. It tries to investigate the vandalism. It tries to find out how damaging this edit was. And it also tries to model the not just the content, but the behavior of the editor. And in this sense, this system allows to revert damaging edits. And what is really funny here is vandals tend to be more involved in edit wars. For instance, you propose something bad, and this bad content has been stored in the Wikipedia page. The moderator arrives and removes your content. You get offended, and you try to remove you try to revert the removal. The moderator gets really unhappy and reverts your edit, and so on. And after a few iterations, this is called edit wars. While benign users, so the good ones, are more likely to participate in discussions. So these behavioral features are used to prevent bad edits again. And how it looks like. Here are some user contributions, and there are some evaluations of the clue bot. So this bot tries to improve the people's life. In order to wrap up this section, we know that wisdom of the crowd-based resources have some content, and this content can be freely edited by the people, but this content is usually quasi-structured. In Wikipedia, you can write free text. It's mostly a text corpus with some quasi-structured information like info boxes, references, links, and so on, headings, whatever. This information needs to be structured. You need some sophisticated parsers. You need some sophisticated data processing pipelines to make a good use of it. If you maintain such a resource, you need to employ automatic quality assurance mechanisms to make sure that you save people's time of the people who maintain the good quality of your resource, because usually you have some editors.
Sorry, I have a question about this current deployment. Whether Wikipedia itself deploys these monitoring systems, or this is initiative of some other users who would patrol?
Uh, both systems that I showed they are deployed by the Wikipedia. So they are kind of official systems that perform edit patrolling.
All right. So
So
and since so this last paper was 2015. So this align is
sorry,
more recent work, maybe on what on patrolling methods.
uh, I have some static in your sound, but if you're asking about more recent work, you can just look at this paper from the order system, and it has a related work section that will show you the review of the previous.
Okay, I see. Yeah, 2020. Okay, yeah. Sorry, I think I missed this reference. Okay, thanks.
So it's something. Okay, also, my slides have some references as well. So I maintain a very comprehensive literature list in the end. So you can freely use it.
Thanks.
Okay, great. So we can take a break, or we can continue. Should we?
Uh, yeah, I think we can go on because it's just maybe half an hour.
Okay, cool.
Maybe
Let's go.
as you wish, we can make like maybe 5 minute small 5 minute break and then return in 5 minutes. Would be fine. Maybe.
Let's return at 40. How about this?
40. Yes. Okay. Yeah.
I think the break is over. Well, so I will continue. Uh, and maybe one more comment about wisdom of the crowds is it's pretty motivating, and it's pretty great that if you do something to Wikipedia or other publicly useful tool, and this and some your machinery or some your systems do improve its quality. So if you can do this for public good, it's great. But sometimes you cannot directly use Wikipedia or something else because you want to be involved in the annotation process. In Wikipedia, you can only count on volunteers, and those volunteers uh, can do whatever they want. But if you need something focused, if you need more specific task, if you need more specific results, you can use microtasks. And to the best of my knowledge, when it comes to crowdsourcing, people are talking about microtasks, and people are thinking about microtasks first. And in microtasks, the requesters create and maintain some batches of tasks, which are called hits or human intelligence tasks, and they can be done by the general public. This is the key idea. If you are a person who knows, for example, the Russian language, and you see some sentence and you have a highlighted word, in this word there's a question like what part of speech is it, you can answer this question, and you just need to formulate your task such that people who have no specific training, for example, they are not, doctors, they are not, for instance, some engineers and so on, they can perform your tasks. And in microtasks, you have usually paid contributors. You pay them through the platform, and the task is usually something really specific, like data annotation, verification, evaluation, and so on. It's usually done on the website with human intelligence tasks. It could be on a mobile application, regardless of the choice. And examples of microtasks are reCAPTCHA. You can remember it. There is a Common Voice initiative by Mozilla, and so on. And the core idea of hits is the following. If you have some task, and you don't know who your annotators are. In order to get some high quality results, you ask multiple different annotators to submit responses. And then you aggregate their responses to get the single and probably, hopefully, correct answer. And in my lecture, I will show you how to do so. So if you look at the picture, you will probably find something really, you know, really that you really knows. And what is it? Any ideas?
Some kind of a capture for
Yeah. So
for protection.
yeah. So, and that's the brilliant idea, and this is what one of the probably most the earliest example of a successful use of a microtask on the web. And reCAPTCHA is a crowd-powered service for protecting your websites by asking people to perform optical character recognition tasks. And it gives the user two words. The one is known, you can just pick it from the dictionary, and you perform some distortions to the image to make it looking like a puzzle. And you have the second word that you don't know, but you obtain it from some optical character recognition of a book. And if you have an optical recognition system, it could has some hard time sometimes. It could have some words in which it's not very confident about. And in order to provide the correct labels for these words, you are asking people to type two words. The first word you know, you just sampled it from the dictionary, you perfectly know what the word is. And the second word is the word for which the answer is not known. And since that a good person will type both words correctly, you will get high quality labels for these character recognition tasks. And what is really funny here is back in the day, 2008, the reCAPTCHA system achieved an accuracy of 99% if the state-of-the-art optical character recognition systems had like 81. So the difference is about 20%. This
Uh,
concept is yeah.
this the standard Google capture with images works the same way, right? So they have like a bunch of images, but they know only labels for part of them. Let's say detect car, and for other part they don't know. Or this is not the case.
I'm not aware of this, but if they surely have some approach to prevent frauding. In particular, I'm pretty sure they have some ranking things that in some automatic way suggest that this is surely not a traffic sign, this is surely a traffic sign, and because otherwise it would not make any sense. I suspect they use machine learning to predict the valid regions, and then they compare your responses with the machine learned ones. So if it's similar, then it's useful. But I'm not aware of how their technology works.
No, but I think they have, let's say, nine segments of images where you don't need really to predict the signal, but to say whether a traffic light is present at all on this image or not.
Yeah, that's
If they
exactly.
know, for let's say, for half of them that they are for sure present, then I guess they can use the same trick to label other three images which contain this.
Uh, I don't know. Well, it depends on their implementation. I'm pretty sure they have some ranking, and I'm pretty sure they just know for sure what is the bad response, and they know, not for sure, but they're pretty sure in which are the correct responses. So there could be some borderline cases that can be avoided by you, but they expect your response matches the ones by some machinery, and they could reuse this information to probably um, evaluate your ranking as well. So this question should be sent by the developers of the system or the current version. I am aware only on the classic system what that was proposed in late 2000s. But the core idea is the same. You have the control object and you have the questionable object, and people submit some responses, and you compare the both responses with the control one, and you if the control one is correct, then you can assume that the second one is also correct. That's the core idea. And of course, this approach is very simple, but there are some more sophisticated methods that also use some machine learning and so on. You can read the corresponding paper. But the core idea is the same. You have some control words and you use them for quality evaluation.
But is it correct that where if I make a mistake for the second word which is not known, the captcha will let me in?
For sure, yeah.
Okay.
And sometimes I've seen some posts on the internet in which people say that, like, oh, reCAPTCHA is very bad. It is doing bad things. But if you look at the words, you'll see that one is looking like generated one, and another one is looking like the real one. So you just type the generated one correctly, and the other one you type incorrectly, and this will let you in. That's true. But when aggregating answers, you should take into account how often you get the particular response for both words. So there is some aggregation technique that will provide you with some single response which is submitted by the crowd, assuming that most people who have this captcha submitted are benign.
Yeah. Okay, I see. I'm asking because this image capture, they ask explicitly to label all image segments which contain certain object. So this is why probably they might be not using exactly the same trick as if you only select a part of, let's say, cross lines, it will not allow you to enter. So they would say, you did not select all of them, please select all of them. So maybe that's not the same mechanic then.
But still, they have some suggestions to the system that says so they have some expectation for the regions to select, and they probably have some expectations for the regions to not to select, and for that I'm pretty sure they have certain assumptions about the correctness of each segment, each of 9 segments.
All right, thanks.
Okay, so an early example of microtask evaluation and application of it was search relevance evaluation on Amazon Mechanical Turk. Amazon Mechanical Turk is one of the earliest large-scale public crowdsourcing marketplaces. It was created, I think, is created in 2001, and one of the early successful results was using it for search quality evaluation. So, given the query, you evaluate the quality of the document matching by some scale. In this case, it's like 4-grade scale, and this will allow you to get some relevance responses. And this saves a lot of time, a lot of money, a lot of effort, because usually when it comes to search quality evaluation, uh, companies are using teams of internal assessors who submit those judgments. In this case, you can use crowdsourcing to dramatically simplify uh, labeling of these query document pairs. There are some platforms, and it's not, of course, something new. Some platforms exist for quite a long time, like Amazon Mechanical Turk, but there are also other platforms like Appen, Scale, Yandex Tolaka, and so on. So you just register there. You can look at the tasks are currently available on the market. You can perform them, and they will pay you money. Uh, and also you can register there as a requester, and you can submit the tasks to be completed by those who uh, perform tasks there. But of course, you can maintain it yourself, and you can set up a crowdsourcing platform on your own if you can gather some people who can submit your tasks. And for this, there are some pretty developed solutions like Bossa, Sometimes I develop my own small platform called Mechanical Sari. You can also use it for some in-house annotation. There are some Prodigy platform from the developers of the Spacey toolkit for Python and so on. So you can use on-premise solution, which requires you to bring some people there, or you can pay for the public crowd that will just take your tasks like any else. If you want to compare them, it's very simple. The managed platforms allow you to submit your tasks and get the responses almost immediately because the crowd is already kind of offered. They are reliable, battle tested, you're not alone there, and it allows you to get some good results in a very short time. Unfortunately, you have to pay for it, and since you are not alone there are some competitions between requesters. Maybe your task would be less interesting for the performers like the task of another requester, and it will not necessarily, but it could sometimes slow you down. And since it's maintained by the third party, you need to take this into account, of course. In contrast, on-premise platforms allow you to self-host them. They can be customized as soon as they are open source, but you need to somehow get the crowd there. You need to maintain it, and there is a lack of support. But the core idea, there are some platforms that allow you to assign tasks, receive responses, and process them. Also, sometimes it's useful to interact with the performers as well.
Yeah, just maybe a comment for the students. So we will actually take a look at both types of the platforms during seminar. So for the on-premise, we will take a look at WebAnno platform for sequence annotation, the task similar to assignment 2, and for the managed platform, it will be Yandex Toloka.
Oh, good to know. Cool. Yeah, so, but when you design a micro task, you need to be very careful about a lot of stuff that could go wrong, in fact. If you look at the image here, you'll see one of the, maybe, of course, it's a hypothetical example, it's a hyperbolical example, but task design in general is a huge issue in crowdsourcing. It's also maybe one of the primary challenges of crowdsourcing, because you need to represent your task such that the performers who are not experts in your field, in your task, could do it good. And it's not about the layout of the forms, not about HTML stuff. It's all about how you present your task and how can efficiently build a mental model for the performer to make it a success. There are also two other problems. Another problem is spam, in which malicious performers who are trying to trick the system and force you to pay money are just submitting random responses, are trying to do other bad things that we are trying to prevent. And another problem is reliability. You need to be very careful with your filters, with how do you target the people and who you want to perform your task as well. And there are some means for quality control. In particular, you can pay a lot of attention to task representation and decomposition. I will talk about it right now. It's also useful to perform some annotator preselection. It's extremely useful to take into account inter-annotator agreement to study whether the people find this task hard or not. And the key idea of crowdsourcing is submitting the same task to multiple performers and the receiving multiple tasks from multiple responses for the same task from multiple performer requires selecting the correct response, and this problem is called answer aggregation. We'll also talk about it a little bit later. The core idea is, suppose you have some very complex task. You need to make it so simple so the people who are not experts in your field complete it correctly. And the key idea of the whole crowdsourcing, initial activities, you just perform task decomposition. That's the number one thing. You split your complex stuff into less complex stuff, and you perform some sequence processing, sequential processing of your annotation steps, and you receive great results based on this. Sometimes you can use the concept called post-acceptance when you received the responses for your objects, and then on the next step, you require the performers to review each other's responses. And then you use these responses to say whether the previously completed steps are correct or not. I'll show you an example very soon. And of course, it's possible to apply some computational approaches to quantify some qualities. We'll talk about it too. And I would prefer to talk about an early successful example of task decomposition, which is really impressive in my opinion. It's called Soylent. Suppose that you have the following task. You have a text, in English, and you want to improve it. Suppose you want to fix, grammatical mistakes. Suppose you want to simplify it. In machine learning and in natural language processing, both tasks are quite difficult. You need some model, you need to deploy it somehow, you need to, it's really not easy. But in crowdsourcing, you can simply obtain really great results by applying task decomposition. And Bernstein et al. Showed in 2010, 10 years ago, that there is a very generic pattern called find, fix, verify that allows you to get great results for very, very difficult tasks using task decomposition of crowdsourcing tasks. In particular, what happens here? Suppose you have a text and you want to improve it. You formulate your crowdsourcing tasks as follows. First, you are asking the performers to find something wrong in your text. They just highlight the regions. Then you ask them to propose fixes to the problematic regions. So you run step one, you obtain some labels, you aggregate these labels, you go on to the second phase on which people propose textual fields which contain some variants of fixes. And as you can guess, the last step is verify. You just asking to select the better edits, the same people who proposed these edits. So they just perform some kind of peer review. And using this peer review, you get a significant improvement over your initial text. In NLP, automatic methods can get in trouble here, but people can solve these tasks simply. And in the beginning of Mechanical Turk, their slogan was something like artificial intelligence. So they simulate the artificial intelligence performance using some human contributions. And find, fix, verify is useful as a generic design pattern that you can use for any open-ended task. You can apply a simple technique, you can perform the similar steps for your task, and you can be pretty sure that the results will be good. And of course, it's not about text, it's about open-ended questions.
This Bernstein, so you have two references, 2010 and 2020. Is this some kind of continuation of this experiment, or?
No, it's all about copyright stuff. It was quite difficult to make agreement with ACM that published the initial paper, so I reached the author and he allowed me to reuse some of his content from his lectures that were organized in the recent course on human computation in 2020. And here's the license, here's the example, here's the reference. So thanks to him.
I see. Thanks.
Yeah, so it's still relevant, it's still very useful, and in my opinion, this is one of the key things you need to know about crowdsourcing. You decompose your stuff and you get great results because people can solve simpler tasks faster than the complex one. And here's the examples of Soylent variations. You can apply Soylent, for example, for text simplification. It's called shorten, some fun. There is a proofreading like crowdproof and arbitrary text processing using something like human macro. Here are the results. For shorten, there are some texts, 5 examples of them, and each between 1 and 7 paragraphs. You so they have written a plugin for Microsoft Word processor, and this plugin deployed tasks to Mechanical Turk. And the median processing time for the text was like 20 minutes, and revisions are like 80% shorter than the original text. And about 100 out of 140 suggestions are accepted at the verify step. So people are actively participating in this, and on the fly, you get your text improved. Another one is crowdproof, which allows you to get some proofreading of your text. And there are some input text with some, intentionally added mistakes. The median processing time was like, again about 20 minutes, and people found most mistakes. The last one was human macro, like, change tense, do some non-trivial text processing. It was not really that straightforward, but uh, the success rate was pretty high. So people did what you want, but about a third of submissions contained an error. However, the results of Solent on very difficult tasks for NLP processes even today are pretty impressive, and you should always think about decomposing your task using, using post acceptance to judge the previously done tasks and so on. It's super effective. But of course, that's not the only thing to take into account when you are running crowdsourcing. For example, you need to, if you pre-select your annotators, if you select those who can perform your tasks better, you get better results. That's obvious. And to do so, you need to estimate the annotator accuracy. So how? And for this, uh, the mechanism similar to the one in reCAPTCHA is used. Suppose you show the annotators several tasks on the screen, and some tasks can be provided. So suppose you have the correct response for some of them. You invested some time in providing annotations, and this allows you to select those who perform your task worse or better. And if you profile them, you get the better results. And you can also evaluate the behavior traces. So some people are using computers differently, and some people use them faster, some are slower, and you can evaluate their behavior to find out how do they perform your task, how difficult is it, and so on. So let me show you an example. A study published past year was about recording traces of those who perform tasks in two setups. The first one is called like content creation, which involved solving captchas. Another one is called information finding, which required some question answering. And the researchers were recording behavioral traces of keyboard, mouse, and so on, mouse scrolling, to find out is it possible to refine and to find out who are careful performers and who are not. And they found that it's possible to distinguish them in some kind of typology, in which some are good annotators, some are cheaters, some are just inexperienced, and you can address all the audiences accordingly. They published a set of features that you can use in your own studies, but let me ask you the question. Suppose you run some annotation in which people submit some responses from some line forms, and what are the features of those who are most involved, who are a good annotator? Any ideas?
I guess those who those judgments or those correlate with some gold standard and with some other good annotators.
Yeah, it makes sense. But when it comes to the user experience and user interface, how do they interact with your annotation interface?
They don't spend 1 millisecond to provide the answer, I guess. So they spend some time to formulate the answer. Maybe that's one of the reasons.
Yeah, exactly. They use mouse actively, they perform some window management, their task completion is not like, 0 milliseconds, they do answer the gold questions correctly, and so on. So based on these features, you should adjust your task when you configure it. For example, if you received a response which was submitted after 1 millisecond after you showed the screen with the tasks, it should be pretty strange, right? But often people who submit tasks, I mean the requesters, forget about it and they hope that everything will be fine. It depends, not always, but sometimes they are correct. And such preselection allows you to increase the accuracy of the annotation result, and simultaneously it will allow you to find out those who need some help. Maybe you have some problems with instruction, maybe you have some issues with some representation, maybe some JavaScript code that you embedded in the task page doesn't work in their browser, and so on. So it will reveal the complexities and the weaknesses of your task, and at the same time it will allow you to focus the crowd to the things you really want to pay attention for. And let me proceed to the computational approaches. So far, as you can see, crowdsourcing was kind of art, right? There are no some straightforward, there are no some maybe strictly formalized processes for task design. You cannot, take some machinery and say, okay, I use this process to obtain my, task decomposition. So far, it's an art and it's not very clear, so it's a great research direction. But there are some tricks. There are some very well-studied methodologies that allow you to get better quality of your crowdsourced data. And I will show you 2 examples of them. First is called inter-annotator agreement. Suppose you have some, part of speech annotation. You have some text, you have some annotators called W1 and so on. And suppose you have their answers. And these labels mean NN is a noun and VBP is a verb. And these tags are from Pantry Bank, which is a very well-known language resource. And suppose you received some annotations and they look like this. And you know that in about 50% cases, the annotators agree with each other. The question is this annotation reliable? Any ideas? Yeah, you can just look at the matrix on the right-hand side.
Sorry, the red means that it's just part of speech which is verb, or
No, yeah, just the color of the label. It doesn't mean that it's a mistake or not. So just the color. It doesn't make any, additional sense.
this is a pretty heterogeneous annotation, right? Because it's almost never coincide.
Yeah, agree. So the performer 1 does not agree too much with the performer 2 and so on. So this annotation is not very reliable because people tend to disagree to each other. But you need to study this, computationally, because you want to automate things that you can automate, and at the same time you need to provide some statistical foundations whether your annotation was reliable or not. It's super important. And of course, this annotation is not very reliable, and you need such a measure that shows that just got one number, that the low value of which shows that your annotation is not reliable, and high value shows that your annotation is reliable. And suppose you have such a measure, and if it's low, it could indicate that your task design has some issues, or maybe your tasks are too difficult to those who perform them. It's a good indicator that should be investigated all the time. And in my experience, the best possible estimate of this is called Krippendorff's alpha. It's a very versatile inter-annotator agreement measure that allows you to take into account missing entries, that allows you to account the disagreement and so on. And it's nothing but 1 minus observed disagreement and the expected disagreement. That's a statistic called alpha. It shows how much your annotators tend to agree to each other. It's chance corrected. It handles everything. It's applicable to almost any kind of data, interval, nominal, and so on. It works really well. And I will show you a computational example of how it works. In the nominal case, so the most frequent case when you have just multi-class labels, it's computed using a coincidence matrix and this formula. Let me show you an example. Suppose you have this data and the algorithm is, you have n annotators, you have n large n tasks, you have some classes, which are the labels. In the example, there are two. And you have your data matrix U, that was the matrix with the label submitted by the annotators. And the output is the number between 0 and 1. You initialize with zeros. Now you iterate over each task. You compute some statistics, which is based on pair co-occurrence. You just perform some additions that depend on the number of the annotators. You compute some marginals, and that's it. Let me show you the example of how it works here. I try to maintain the notation closely to the one described in the book by the Klaus Kippendorf. So they are using new matrix that is transposed. I have to make this clear. So this is a transposed matrix, but query is the same. Since you have only two responses, noun and verb, you initialize with zeros, and you start processing each task. You compute how often people tend to disagree with each other, and after a few iterations, you obtain this matrix for all the responses. Now you compute marginals, and after that, you found that your annotation is not reliable. Super useful. What is really amazing about alpha is that it's a single number, which is versatile, it's chance corrected, and you can guess based on it whether you have a problem or not. It's super useful. It's a super useful indicator.
Sorry, can you maybe just elaborate a bit on this expected interpretation of this expected disagreement? So, like, what is supposed to mean? So, like, the harder the task, the larger will be this number in principle, or I'm not sure I got completely how it's so calculated on the slide number 38. So it's basically square of NC, and NC is what is the number of all categories, or what?
So you need to think about it as follows. Suppose you have a perfect annotation. In this annotation, every annotator submits the same responses as the others. And suppose you have a perfectly imperfect annotation in which every performer, every annotator disagrees with each other, right?
Yeah.
And alpha is nothing but this. You compute how much disagreement you can have in theory. It's called DE.
Okay, so DE would be the maximum possible disagreement among all the annotators.
Exactly.
And if, but wait, so if observed disagreement is exactly equals, then we have zero. Okay, yeah, then we have zero worst case, right? And if we have no disagreement, anyways, this term cancels out. Okay. And could you explain this OCC, meaning this coordinate value OCC? So OCC is an element of a square matrix which composed of a set of all classes on one hand, set of all classes on another hand, right?
I think O means observed. So you are building a coincidence matrix, and this matrix elements contain the amount of disagreement you observe. Let me show you the next slide. No, this one. That wouldn't just show you the bad example. Look here. In this case, the agreement is perfect, right?
Yeah.
Everyone tends to agree to each other. And on the next task, right, there's disagreement. There are some formulas on which it's computed, so there are, basically some permutations of pairs in which some match each other, some don't. And the core idea is you compute how many pairs don't match, because there is surely a mismatch here. So there are some verb votes, there are some noun votes, in which you just add the amount of disagreements between pairs adjusted by the number of annotators submitted the responses. And
This
you do.
P, so this is probability of.
It's not probability, it's the set of pairs,
Okay.
two elements, provided from this row in the matrix.
So the two, so you have this matrix. What two means? Two means that there is two disagreements
No,
in this
it's
row.
permutation of two. It's two permutations. So you have some pairs of responses between W1, W2, and so on.
Mhm.
You obtain some set of permutations, two permutations, because you need pairs. And you count how many pairs you have with agreement and how many pairs you have with disagreement.
Pairs. Okay, so maybe clarify once again. So the pair in this case is T2, one pair of T and W, or this is something different.
No, it's like
About which pairs we speak here?
it's like, for instance, T2W1 and T2W4.
Yeah. Okay, this is one. So
This
this
is
is
the
one
response.
pair. One cell of this table is one pair.
Yeah.
Okay,
No,
and
no, no, it's not. No, sorry. You have four elements, and you create four. So you compute all two permutations of the set, and you compute how often these pairs match to each other. In which case, how many cases you have in which the responses are the same, and you fill in the corresponding elements of this matrix, and that's it.
okay, okay. So this matrix O. Okay, so just to clarify, so this 2, 4, 4, 2. The meaning of each of these values is computed on the basis of the number of permutations,
Yeah. So,
which.
well, there's a response like you have each possible non-missing pair of response, and you count how often you have the match of an n and an n, and how often you have a match between verb and verb, and this noun verb noun, something like this.
Mhm.
And after iterating over each task, you get this matrix uh, as the addition of elements of this matrix. And after this, you compute marginal values, which allow you to quantify the disagreement.
Okay.
So after performing this, look, yeah, there's some prior agreement on verb. Here is the same figure as on T2. And after that, you receive the matrix O. The matrix O contains the disagreement between, no, not between, but for each label you have. Each row is one particular label. You just add them, you compute the marginals, and you compute the number of elements, and that's it. You compute you compute the disagreements, and if you subtract from one this rate of disagreements, you get the alpha for nominal values.
Okay, thank you.
Great. So the key issue here is how to interpret it. The author of alpha recommends the following approach. If your alpha is strictly larger than 0.8, you have a pretty reliable annotation. There's a very important comment that reliability of the annotation does not imply correctness. This means that people tend to agree to each other. They could be agreeing in the wrong responses, but they tend to be, you know, reliable. So if your alpha is larger than 0.8, you're doing good. Otherwise, if your alpha is smaller than 0.8, but it's larger than 2/3, you can make tentative conclusions only from your data because the disagreement is high enough to be concerning. So you need to recheck everything. And if it's less than 2/3, you have issues and you need to stop and start thinking about what went wrong. Of course, you don't have to program it yourself. There are some pretty battle-tested implementations for Java, R, Python, and so on. Yeah, you can use it, and um, I recommend you to use it every time you have some issues and you have some studies on data annotation and data labeling in which you can simply compute this untraitor agreement measure to study how good are you doing. If you want to learn more, you can read the paper by Arstein from 2008. It's a very comprehensive survey which is still topical. And there is a case study on agreement and disagreement, which is really interesting in the context of NLP evaluation. There is a very, very well-known task called topic modeling. This is a task when you have a corpus of documents, you have some text, and you perform some statistical manipulations to extract topics. A topic is a set of words that represent some theme, like, this topic is related to some computing, the second topic is related to some selling, and the third topic is related to some theater, film, play, whatever. And then, since you got these topics, you are providing every document with the kind of label or the composition of these topics to learn what's your corpus all about. And it's very hard to objectively evaluate the quality of topic modeling because it's an unsupervised model, and you need some gold labeling in which it's really difficult to obtain. It's really difficult to come up with some really good idea how to evaluate it automatically. But using crowdsourcing, you can simply apply some disagreement ideas to provide reliable evaluation of it. And it was from Neurip's paper from 2009, in which the authors proposed the concept of intruders. Suppose that you have a topic model trained on your text corpus. This topic model has some topics, which are sets of words, and you need to evaluate them first. Suppose you have a topic, which is a set of words. In topic models, the words are usually ranked. There are some weights. And suppose you can add a random word to the topic. And the idea is, since you have the set of words to rank, they are already ranked, you take the top 5 and you insert one more. And you insert the word which has a high weight in another topic, but probably a low weight in this one. You perform distortion of your data. And the idea is to ask people, don't you see anything strange here? So you ask people to find out the intruders. The core idea is, if the votes for the bet element matches the intruder, then you are doing good. Otherwise, you are not. The same idea goes with the documents. So topics models provide topics and matching to the documents. And you also need to evaluate how topics match to documents, in which case you provide the annotators with the text and some abstract of this text, and you select the intruder topic that is not relevant to this entity. And you compute the topic log odds between the human judgments and model judgments. And what is really cool here is this very simple task allows you to get objective evaluation of your topic models, and these evaluations do not correlate with the machine ones. Usually topic models are studied using perplexity measure and so on, In this case, topic models are evaluated by humans, and humans propose different results than you obtain using perplexity. And they find if your intruders are, if they find your intruders are the really incorrect elements that you proposed, you are doing good. Otherwise, you have some issues, and you can take into account this and um, adjust your method accordingly. And this idea can be used in really different setups. In particular, we have once upon a time performed a similar study in which we were trying to build some distributional semantic classes. There is a LREC paper. Suppose you have a set of words. Suppose you have, like, apple, mango, and so on. These words usually describe fruits. And you want to evaluate how correct can you build the set of hypernyms. So the words like fruit, some other words related to fruit, and so on. So higher level topics. Not topics, but the core idea is the same. And you want to make sure that your method produces correct data. And we used crowdsourcing. We used the following formulation. Suppose you have these topics, and suppose you have these words, and please select the incorrect ones, the words that do not match these three topics. So there are topics, there are words, and we intrude the incorrect ones, and we are trying to find out which are also incorrect. So we expect that in a good set of words, only the intruder will be selected. In a bad set of words, most words will be selected, not just intruder. And for this, we used accuracy and badness metrics. Accuracy is just the fraction of tasks which were correctly identified as intruders, and badness is just the fraction of tasks for which non-intruder words were selected. And we found that this annotation was not that reliable, but generally it allowed us to get some tentative ideas like, okay, this method probably has some issues, and we can use these conclusions to find out which variations of this model performs better. And in this case, if the accuracy is pretty high, we can use this, and we can evaluate different aspects of the model, both the clusters, the words, and the hypernyms, the topics, as follows. And we found that this approach allows us to find the weak points of the method, which is really important. And if we need that, we can make a pause, but I can go ahead and proceed. And any questions so far?
Yeah, maybe we can make a small break. So I think I don't have questions, but maybe somebody in the chat. Okay.
So maybe 35 minutes or earlier?
Yeah. That's
35, okay, cool.
Clarify once again about this Creependor's alpha. So can you go back to the example? So just to understand once again, so we perform processing task by task, right? So at every step we take a slice of these metrics which correspond to responses of different workers on a given for a given task, and then we get this number of permutations only for this particular slice, right?
Not exactly.
This p so I'm still a bit confused, like this notation p. So p is you show now this row or vector on the slide. So in this case, this set of permutations, what it will be in terms of these tags and n and vbp. Sorry.
So you compute all possible permutations of a set. Let me show you from the algorithm. So you take the row of your matrix. So a row is a
Yeah,
task
yeah, yeah, sure.
formed by several annotators, and for each element, for each pair of elements of all the possible permutations you got here, like and then and then and then and then and then you count how often they just matched. So you say that in this case, I have like 6 pairs. This one, dub1, dub3, dub3, dub4, and dub4, dub1. Uh, and all these pairs are directed. They are, they are ordered pairs. They are not unordered. And since you have ordered pairs, and all these pairs have the same label, and this label is corresponding to this element of this matrix for this step. You write here 6.
Yeah, I see. So,
And the same process, happens all the time. So you compute all the pairs, and then you distribute the pairs by their labels as according to the label positions in the matrix. And then you just weight all the matrices by the number of performers, the number of annotators minus 1 who submitted these responses. That's the
and the
correlation.
meaning of MC, so this constant, what is the meaning of this then marginal vector?
Uh, it shows let me see this formula. It just shows how much expected disagreement, or in this case, agreement. So you compute expected disagreement in the denominator of this fraction, right? The denominator is like expected disagreement, and the marginals show the expected agreement for every label you have.
Okay, yeah, I see. Okay, thanks. Now,
Okay, it's actually a pretty fun exercise if you implement it yourself, so highly recommend it. And when I show pseudocode, it means that you can spend some time, and maybe if you have spare time, to just implement it. And usually it's a fun exercise in which you can learn a lot about how things work. But now another computational approach, another extremely important computational technique that allows you to get most quality of your data, which is called answer aggregation. And as you remember, the core idea of microtask-based crowdsourcing is submitting the same task to multiple annotators. This gets you in trouble of choice. You need to choose the correct label for each task. And if you look at the example you see before, you have multiple answers for 4 tasks. Some annotators just, prefer not to submit responses for T1, but the core idea is you have multiple responses. How to select the right answer? And of course, there is a very obvious approach that you already know. My question is now for you, which one?
majority vote.
Yeah, probably you have seen the slide or you knew it
No,
before.
actually not, but
But the exact term, you just know the formulation. It's not fair. Okay, the core idea is, suppose you can treat every response as a vote, and you simply count the number of votes you received for every task, and the most frequent response is the correct one. It's an extremely robust strategy, and various studies of crowdsourcing aggregation say that majority vote is a pretty robust baseline that is sometimes not very trivial to beat, which means that majority vote works well, but it has a problem of ties. For example, look at task 2. It has 2 votes for noun and 2 votes for verb. And my experience with playing with aggregation methods and sometimes teaching them is if you simply aggregate your responses when you have a tie, you must break the ties randomly. Otherwise, you are making preference to some particular response, and your overall quality would be worse. So it's just an empirical fact. You must break the ties randomly in order to ensure fairness of your method. But another problem is this matrix already shows some agreements and disagreements between the annotators, as you have seen before. And what if we can somehow model these expertises of the performers, and what if we can use this expertise estimates to weight their responses and to get the better results? Suppose, before I continue, suppose we have this A column, which corresponds to the majority vote result, but the correct responses for this data will be like this. The first task is noun, the second and third are verbs, and the last is noun too. Which means that if you already knew this before you start annotation, you will assume that performers 2 and 3 are the best ones, right? And the performers 1 and 3 and 4 are not that good. And this is the motivation of creating more sophisticated aggregation methods. And funnily enough, amusingly enough, one of the most efficient aggregation methods for crowdsourcing was invented before the crowdsourcing was invented. It was invented in 1979 for medical analysis and the processing of their results. Suppose you have some patient, and this patient is examined by multiple doctors, and each doctor provides their own judgment, and you need to aggregate their responses to find out which diagnosis is correct. And this formulation extremely well fits the crowdsourcing scenario in which you have some incomplete data, in which you have some mistakes and so on. Everything happens. And this probabilistic model allows you to model the correct answers for your tasks. And this model just performs modeling of error matrices of the annotators, and also models the probability of observing each particular label, and it uses these error matrices and probabilities of observing labels to infer the correct responses. And suppose you have this this expression. So this Nyj k is 1 if the performer k answered the label j for the task t. And here comes the pseudocode that you can, in your spare time implement, and you will get exactly the same results as I have. So I tried to keep closer to the notation in the papers, so it don't get really different, but the core idea is the same. First, you initialize your responses. So you need to compute the probability of observing each response for each task. You initialize with majority vote. So you just compute how many times you've seen verb, you compute how many times you see noun, and you just normalize this by the number of other votes. Now for each label, you perform some matrix manipulations, and you construct confusion matrices for the annotators. Then you recompute the priors, which are the probabilities of observing labels, and you use these estimates for the matrices and the label probabilities. After that, you recompute your probabilities of observing the responses, and eventually the algorithm will converge, because EM algorithm always converges to a local optimum. And of course, if you compute the likelihood of your model, which is available in a closed form solution, not closed form, but in analytical solution, which is really simple to compute, you will find that on each step of the algorithm, your likelihood will increase. And to aggregate, you simply choose the most probable labels for each task. And I have a computational example for you. Suppose you have this input, and you have seen this before for a lot of times. You will recognize that you have the following counts. You are starting with counting the labels and the tasks. You see that this one was noun for 3 times, that was 2, 2, and so on. There is some disagreement, and we will take into account this disagreement. You provide some normalization of these numbers just to obtain the kind of probabilities. You see that this task is for sure noun. This task is not for sure anything that we have, and so on. And we want to gather better data, better results from the same data without any additional annotations. And David's King model allows you to do this. You are trying now to compute the error matrices of every annotator you have. For this, you take the column corresponding to the annotator, and you initialize the error matrices with zeros. And then look what do you do? You take into account this column, and you take into account the matrices with the probabilities of the responses. But look here, this performer, this annotator, said noun. And we know that nouns for these tasks have probability of 1, and the verbs have the probability of 0 for the whole data set. So we add noun to here and 0 to here. So we add this row to the column that corresponds to the noun. And before I go, let me remind you that error matrices are matrices in which that show how likely this classifier or this annotator or anything else does a mistake. For example, if the correct answer is noun and the annotator says it's noun, the probability or the being sure in this is 1. And other values on the main diagonal are the correct responses, and anything else is not correct responses. Now we compute the error matrix for the annotator 1. We found that this value corresponds to this row, and we add this row to this column to us because we want to model how often we observe the correct response, which is indicated somehow by this number 1, answered by this performer 1. Okay, so far so good. Another step, another addition. In this case, we're not that sure. Now, this time we are received the response of verb. We add these probabilities to this column because this time the actual response from the performer was this. We repeat this again, and we obtain the matrix of some numbers. We normalize it, and we get the probabilities of the responses submitted by the first annotator. And we see that this annotator has pretty decent performance on verbs, but well, the error rate is pretty high. You can compute accuracy just by dividing the trace of the matrix by the sum of all these elements, and you get the accuracy value. But the core idea is you now receive the error matrix for this annotator, and you can predict whether this annotator makes a mistake in all the labels you have. You repeat this process for all the annotators. And having this step performed, you get the set of matrices, and each matrix shows some examples of wrong results. And you see that some annotators are more correct, like the annotator may be 3. Some annotators are less correct, and you can actually see how often they do mistakes. Now you estimate these matrices, and you now need to compute the probability of the classes. To do this, you already have your probabilities of receiving the response noun for task 1 and so on. You simply add them to each other and normalize. And which means that you, with the probability of 56%, you obtain the label n for any task. And similarly, with the probability of 0.44, you obtain the verb label for any task. This is needed to make the model sound. Now you are Well, now you say, okay, I have already computed everything, and let me try to guess the labels from the error matrices I already got. So I can predict how correct my performer will be, and I know how often I can receive these responses. And let me use this information to make predictions. And in order to do so, we forget everything about our actual data or about our actual counts. We simply use these frequencies, these probabilities to as the initialization values, and we simply multiply the rows of the error matrices by the columns of the error matrices by the rows of the answer probability matrices. We perform these multiplications, and this time there is no response. This time there is response. When got the matrices, we need to normalize them, and we got the aggregated responses. And you can trust me that if you repeat this process until convergence, you will get these results. If you don't trust me, you don't have to. You can implement the algorithm and you'll get exactly the same response, but maybe you will have much more numbers after 82. You'll get some difference in rounding and floating point representations. But generally, you'll get this very same results that show that using this data, using the same data as the majority vote, you can get better results, you get better orientation by applying smarter algorithms that takes into account the internal structure of your data. So you learn the error matrices, you learn the uh, label parameters, and you can use this information in other contexts. And as soon as you perform all the steps, you can terminate after the convergence, and your aggregated responses will match the goal responses in this case. What is really great about, for example, David-Skin model and other models that have that are probabilistic, they model the world as according to some representation, to some model, and you can use parts of this model after aggregation to do something fascinating and truly amazing. For example, you can use the error matrices of annotators to do something called repeated labeling. It's when you when you decide whether you need some more annotation labels or not. So you can judge whether you need some more data or not. It's super efficient. It is very, very, very useful. You can use this data for dynamic pricing just to estimate the optimal price for the task. And it also uses these models. You don't have to implement it yourself, but there are some implementations that are already available. Some can just be run on your computer, like Square in Java. There are some other ones like Spark Crowd, which is a distributed implementation of the same techniques. There is a wide variety of various implementations and various methods that are different due to their assumptions, but the core ones are David-Skin, GLAD, Karger, or SHA, and so on. These methods are different, and you need to select your model based on your data, but the core idea is the larger data set you have, the more parameters you need to tune, and the better. So if you have a larger data set, you would need probably more the method that has more parameters. And
sorry, can you explain a bit how this plot was computed? So we have probability of the error and then the number of assignments per one task. And this, yeah, how would the setting would be for this?
This result is from the paper by Karger et al. It's published back in 2014, but the picture was available in their preprint published before. The core idea is they were designing a method that aggregates responses. This method has some assumptions and optimality guarantees, which is amazing. But in order to evaluate your method, you need to perform some experiments. And this is one of their experiments based on, as far as I remember, on a synthetic data set. In this case, they show you that if your crowd performers, if your annotators has a large probability of error, so they could be sloppy, they could, they might not get your instruction. The reason could be very, very different. If they are not very accurate, regardless of the reason, you can see how it affects the quality of your aggregated labels. And if you look at the axis X, the number of assignments per task, the number of assignments per task is the number of people that submit responses for your task. Sometimes it's called task degree. So for example, there are 4, 8, and so on. And look here, given the same crowd of the same quality, you compare several aggregation methods. One is called majority voting. Another one is called iterative algorithm. It's the algorithm of Carr-Gerdoll-Coss. And expectation maximization is, as far as I remember, David Skin. And you see that at some point, no algorithm performs better than majority vote in some case. Just look, if you have majority vote and you have enough number of responses, it works. It doesn't work that good. But at the beginning, if you have a lot, if you have a very small number of performers per task, majority vote is a super robust baseline that is really hard to beat. And this is the core idea. That's the probability of error, and this is the number of tasks per performer, and there's some synthetic.
The probability of error is computed as a fraction of correct predictions with majority voting with respect to like gold standard, correct?
Yeah, that's kind of that's surely a gold standard, and there's a probability as according to this gold standard. Yeah.
Okay, and I had another question about the previous algorithm. So you told that there are some theoretical guarantees of its convergence, right? So we can, but so this is a variation of EM algorithm, and EM algorithm would converge to local optimum.
Exactly. Yeah.
So not global. So then this means that it's theoretical guarantees to converge, but not converge to global, but to some local optimum.
Indeed, yeah. That's the core property of the algorithm. It performs the optimization of your model, and it, of course, converges to a local optimum. So it could be not the global one, but it will stop eventually, and it will stop eventually to some reasonable result.
So this property of this approach is stemming from the fact that it's a direct application of EM algorithm, and the EM algorithm has this property, right? So there are no additional like twists to make it work. So this is just a formulation of the task. So okay.
Yeah, that's the classical application of a probabilistic graphical model that says you see the world is like this. You have some labels. They appear with this probability, and these probabilities affect how. So these probabilities affect the responses provided by the annotators. And these responses are also affected by the probability of error made by the performers. So you recover the hidden label, the hidden variable, which is the correct answer. That is, and the whole method is focused on this task. So it's a direct application of EM, and it was invented back in 70s, end of 70s, and there were no, very widespreadly available computer machinery that can, crunch numbers.
And for this a priori robustness or reliability of one annotator in the beginning of this algorithm, we can we specify some a priori maybe this is something I missed. So let's say we know that from the history of other tasks that some annotator is performing good usually, and other is not. Is it possible to somehow use this to initialize this process?
It's done implicitly by computing these probabilities. Before you start, you compute the probability of observing this response to this task. And if the responses submitted by this annotator diverge from this, it will be surely affecting these metrics W. That's the core idea.
Okay.
I mean, you can always make the model more sophisticated. You can add more parameters. You can adjust the priors and so on. But this is the classical formulation that is really straightforward and simple to understand, use, and implement.
Okay, thank you. So from the last
Maybe
plot
one
to
more.
show us, so this still, I mean, with this evaluation, it's still what is the main conclusion that if you have, let's say, a few annotations, it might be still not sufficient to uh, enable the advantages of these algorithms, or maybe in some other tasks, it still makes sense to apply these algorithms and not the majority voting.
Our general advice is to use Daviskin all the time. It is robust and it works really well. However, if you have a tiny data set, like is composed of a few tasks performed by several annotators, the Daviskin model will have not enough data to converge to a reasonable result.
Mm-hmm.
So it will be similar to majority vote, and it's usually pretty robust. But of course, if you have a huge data set, the method that has a lot of parameters will perform better. If you have a tiny data set, you usually can be successful with not that much, with not that huge amount of parameters. You can think about this, like a neural network. If you want to train a neural network, you need to have a large amount of data, but if you can just go on with naive bias, you can have a smaller amount of data. That's the core idea.
So not only the number of assignments per task matters, but also the number of the size of the data set, right?
Yeah, of
Because
course, but yeah.
this plot only shows the number of assignments for some fixed data set, but you say that, okay, another dimension also matters a lot.
Yeah, everything matters, but I would say um, at some point you can find that you can limit the number of assignments because the probabilities you obtain from the Davidson model or other probabilistic model for answer aggregation is high enough that you can stop. So there is this procedure is called repeated labeling or incremental relabeling that just uses these error matrices and uses these aggregated uh, parameters to say that, okay, this example is well annotated. You don't need a response for this one, but please take into account this one. So,
Okay, so yeah, thanks.
cool. And this was the most hard session. And let me show you one more example of using this. This is an example of using the whole microtask-based stuff. I demonstrated in the last maybe couple of minutes. Once upon a time, we were interested in organizing a shared task in which we want to learn how well can we disambiguate words in sentences in Russian language. And this was the first time such a task was organized, and we were the organizer of this task. Uh, Well, the problem formulation is this. You have a sentence or a context of a word, and you need to predict its meaning. For Russian, the available data sets are not, the number of available data set is not that huge, so you sometimes need to came up with your own data set. And that's why I started doing crowdsourcing, because I wanted to make sure that I can gather all necessary language data for my studies. And that's the same reason I started doing clustering and other things. So I wanted to bootstrap my studies. I want to bootstrap my data sets so I can successfully apply some methods to make sure that I am doing the right thing. And you now don't have any data, but you have some raw data, and you need some annotation. So this clearly a data annotation task. Of course, there are some dictionaries of Russian. For example, the large explanatory dictionary. In Russian, it's called Большой толковый словарь. We just took the subset of this data set and tried to apply crowdsourcing to find out how it works. Since the task was all about the creation of a gold standard for a shared task, so it needs to be of very high quality, we got 9 annotators per context in order to benefit from all those aggregation methodology. We limited the annotation speed, so we don't receive fast responses, and we limited the number of answers per annotator because we don't want the single person annotate everything. We want some variability of opinions. And we used Davidson aggregation algorithm to aggregate the answers. And the pipeline, the whole pipeline of data preparation and data processing and labeling was like this. We have chosen 20 words from this dictionary, and we sampled their contexts. Then we prepared some context for training the annotators. The core idea is you need to preselect your annotators. And to preselect them, you annotate your data manually. Of course, a subset of your data may be 10% or whatever. And you perform and you submit to them the training examples. If they fill in these examples and if their responses match to yours, you can allow them to complete the tasks for money. So we were pre-annotating data. Then we just started annotating about 2,000 examples on the platform. We were tipping for feedbacks and error reports, which were really important. There are some bugs. And then we manually curate the results. Because this is a gold standard data set, we really need to make sure that the data is correct. And the results were this. The whole annotation of this amount of data took about less than an hour, and the Kirpendorf's alpha was pretty high, so it's like 0.83. There's a lot of agreement here. And the task design was like this. You have the context, you have the selected words. These words are links to some popular search engine that will provide you with additional context if you need so. And there are some predefined possible meanings extracted from the dictionary that we had. And the performer just submits response for every task and clicks this yellow button called Отправить or send. And that's how we gather the data. And we had to curate the data set because we really need high quality data. And our experience showed that we made about 5 changes after reviewing the data, which is pretty good. And since the Davidskin model provides you not just with the aggregated labels, but with the confidence, since you have the probability of this label for this task, you can just make sure that the responses with low confidence need to be curated, and we curated them, and also some of the high confident values. However, other data sets and the rest of this data set were annotated by expert linguists, but crowdsourcing allowed us to complete the annotation in minutes. But these experts were annotating data for a couple of weeks, as far as I remember. So we get the quality comparable to the experts in a fraction of time, which is great. And you can use and download this data set under a permissive license using the link below. So to wrap it up, microtasks are probably the most popular approach to perform some data labeling and label collection for NLP. And you should always listen to the feedback you get from the annotators. There is no excuse for not computing and reporting the agreement, because if you don't, you probably don't know what you're doing. You need to know what you do. Crowdsourcing usually offers some means for quality control, like aggregation, some filtering. You should use them, otherwise you will be in trouble. And of course, there are so many things to improve that you can write a lot of theses based on this topic. Okay, and next section. Should we take a break or not?
Yeah, maybe a small break would be good.
Okay, so let's continue in 15 maybe.
Yeah, all right.
We were talking about wisdom of the crowds, like Wikipedia. We were talking about microtasks, like Amazon Mechanical Turk and so on. And here is how you can use another perspective of crowdsourcing to gather data, but this one implies video game development. So you are trying to design a game such that you receive labels, and a good player, a fair player that wants to win, submits labels that are useful, and you incentivize this behavior. So usually it's all about volunteering, and it's all about video games, and it's all about data verification manually. And historically, one of the earliest examples of crowdsourcing was a game developed by the same person who invented reCAPTCHA. So let's have a look. Suppose you want to annotate images. You have an image, and you need to provide a set of labels that describe this image in some way. And this person and the team of the researcher created the video game that was played in a browser. It's called the ESP game. And ESP stands for extrasensory perception. You go to some website, you click the button like, I want to play a game. You are matched to some other person who wanted to play the game too. And you have this interface, you have this image, and you have a set of taboo words, which mean that we know these words, don't use them or you will be punished. And your goal is to submit the words that describe this image, and you get some points if your labels match the ones submitted by your not the opponent, but by another player that participates in the same session with you. So, and for a lot of matches, you get a higher score and so on. And this game allowed you to provide some additional labels for the images. And mutual agreement, of course, indicates the success. Disagreement doesn't. And the experiments show that about 85% of the words were evaluated. So the results of this experiment were evaluated, and those who were evaluating this said like about 85% of the labels we have are useful. So which is pretty impressive, because we don't have to use some difficult machinery like computer vision and so on. We just use crowdsourcing in some smart way, in some clever way, to provide and gather labels for your data that you didn't have before. But let me show you some more examples, and these examples are relatively modern. There is a language resource, a semantic network called BabelNet. It's a large-scale multilingual knowledge base that contains some knowledge of words, their relationships, their sets of synonyms, and so on. But a language itself is a thing that changes every day. And how can we improve the coverage of this huge language database? We can try to ask people, but sometimes it could be boring. And what if we can, design a task, design a game that will be funny and at the same time useful? And they designed a couple of games, and I will show you one of them. It's called Infection. And suppose that something bad happened, and people are trying to save themselves from zombies. And they have came up with a solution. They have just chosen a word like medicine, and here's its definition. And you need to go to the battlefield, as presented here, and you know that those who scream the words related to medicine are good people, and some of those who shout something not very related to medicine are not good people or could be zombies. So by shooting them, you will get some points, and by screaming the correct words, you are also incentivized, but if something happens, you get shot. And there are some weapon upgrades and so on, and you use this mechanics, game mechanics, to check whether the new words we have are related to this topic or not. And it's a multiplayer game, so there are multiple players that participate in the same session, which is pretty great. Yeah, but what about the quality of the annotation? Of course, game development is a very, very, very difficult task because it requires you to do anything. It requires you to write, to prepare some assets for the game. You need also to use some game engine to implement these game mechanics. You need to provide some data. It's a lot of work to do. But they tried two variations of this game. One is called Infection Free, in which you can just join the website, play the game. In another setting, they have paid for this interaction. So you are paid for playing video games. Why not? Another example is performing the same tasks on a microtask platform called Crowdflower. And here are the results. So free version of the game yields high quality annotations, so the quality is good. And of course, you don't pay the annotators for their submissions, for their contribution. Of course, the development itself requires some effort and requires some investment, but it's not a direct cost. It's, like capital expenses. If you pay for playing your game, it also works quite well, but it's more expensive than running a Crowdflower task. However, volunteers, of course, make less mistakes and provide more consistent answers. So they are motivated by the game itself, and you you receive better responses by letting those who want to play. Any questions so far?
Regarding just game mechanics, you had so these zombies which yield irrelevant words, they are not players, right?
Yeah.
They are just generated automatically.
Yeah, so let me show you the screenshot first. The core idea is some non-playable characters could look like the regular players, but they could be infected and they are screaming something irrelevant. So they are zombies who are just, things to shoot. But there are some infected NPCs. And these NPCs scream something irrelevant, but they look like the regular players. And you need to get rid of them before they get you infected.
Okay. So.
It's, it's 2020 and it was in 2014. No relevance, no. Don't repeat this at home. Yeah, so this is the case of game development, and this is the case how game design and video games can provide you with some labels. There are a myriad of other examples, but I was most impressed by this one. As according to my experience, you can employ some gamification mechanism to improve the quality of annotations, even in other genres of crowdsourcing. And what if we can use gamification and some team-based stuff to improve the quality of annotations in other cases? And I was studying the case of OpenCorpora. This is a large open annotated corpus for Russian, and most annotation work was done for morphology. It's like part of speech tags, cases, verb, forms, and so on. Yeah, and the idea is that there are some freely available texts on the internet. They are initially parsed, not parsed, but tagged by a morphological analyzer. There are some ambiguity that is not addressed by the analyzer. They are uploaded to the crowd, and the crowd provided the responses. Of course, these processes volunteer-based, and this corpora, this platform uses their own platform, their own system to receive labels. It looks like this. There is some sentence set, there are some highlighted words, and you need to specify the case of the noun used in this sentence. As soon as you have selected some of them, you just click I want more, or thanks, I'm done, and that's it. So you can use it, and you can provide this annotation even now. But my interest was, once upon a time, they have run a team-based, not just competition, but they allowed the participants to join teams. And I was curious whether it helps the annotation or not. So I just evaluated the statistics. I evaluated the performance of the team, of the teams, of the individual performers, and I just tried to investigate the largest team, and I found that an average person who is in a team provided more annotation than an average individual contributor, which allows us to get more labels from those from the same amount of people. And this effect allows you to get more data with hopefully with a better quality. So you use gamification to gamify to improve your process of annotation that you already have. Of course, to summarize this part, creating games with a purpose is difficult, but they do attract the annotators. You get some people who voluntarily will submit your responses. They work better when they are free. And of course, the quality control mechanism are similar to the ones in microtasks, but they also require some anti-cheating machinery. And it seems that gamification is a useful option, but if every annotation project will abuse the same mechanism, it will get bored. So you need to maintain some balance and have some vision how to not abuse this, because otherwise it could be problematic. Okay, that's it with the previous part. Any questions? Okay, so we're almost there. There are some last minute advices that could be useful for your further journeys. So if you want to choose the genre, you need to ask questions, and here are the answers to your questions. If you can afford paying, just stay with microtasks. They work really well. You will get support. You will be not alone. It works well. If you have a lot of spare time, for instance, if you are a student, if you have, you just, like programming, software development, you can try to write your game. You can try to deploy your own annotation system. It would be a great fun. So highly recommend it as soon as you have some spare time. If you want to produce the content, but not annotating it, just stick to the Wikipedia similar stuff. So you provide some common platform that allows people to collaborate, to contribute some stuff, and to edit each other's changes, which would work great. But the primary issue of crowdsourcing that I mentioned at the beginning of my lecture is the applicability of crowdsourcing. There are some tasks in which you need some expert knowledge. You cannot, for instance, make medical decisions by the judgment of people who are not doctors. There are some other special disciplines, and if your tasks require some special skills, probably the public crowdsourcing is not for you. You can gather private crowd, and you can use some, on-premise systems to process this information, but probably public crowdsourcing marketplaces is the wrong choice for you. So don't use crowdsourcing for anything that strictly requires expert knowledge. But one fun experiment that I did 5 years ago was this. Of course, the websites are not the only available medium on the internet. The internet is huge, and the World Wide Web is, a part of this huge phenomenon. What if we try something else? And back in 2015, Telegram, which is a popular messenger, just rolled out the bot platform. And I was thinking like, okay, I have Mechanical Sar, which is on-premise crowdsourcing platform engine. What if I allow one to annotate data using Telegram instead of web-based interface, which will reduce the barrier to entry. It will allow more people to participate in the annotation, which in my opinion is great. It just, make the things simpler. And I just created the proof of concept called Telebayarin, and, don't ask why. It worked like this. You just add some bot, and this bot say like, hi, let me start the annotation. You send this comment, and this bot this bot is using the Telegram facilities for user interface. You can provide some choices. You can provide some selections. It says like, what do you want to annotate? This one or this one? There are some projects. Each of them is different. You say, okay, I want to annotate this one. Now you get some tasks, and you get a convenient form to submit your responses. You choose the response, say yes or no. It receives them, and if you want to stop, just say stop. And you are being appreciated. However, you have submitted some responses to some crowdsourcing platform. Yeah, so that's how it works, and this was a really funny experiment to organize. I think this is the last thing I wanted to say about crowdsourcing itself. Now I would like to tell about some meta stuff. If you want to learn more, there are some journals, conferences, and books. This year we are organizing a crowd science workshop at NeoRIPS, which is the main conference on artificial intelligence. We are also organizing a bi-weekly crowd science seminar. I will send you the link after I finish the lecture. Today at 8 p.m. Moscow time, we have another instance of the seminar in which we will discuss a paper published, not published, but accepted at Semantic Web Conference 2020. It was all about gathering knowledge base with questions and answers for Russian. It was a pretty challenging task, and I think you'll enjoy it. There are some books to read. All of them are great. There are some other courses and tutorials specifically designed for crowdsourcing, including the ones organized by us. There are some crowdsourcing and crowdsourced datasets available on the internet. And here comes the conclusion. I believe that crowdsourcing is a great tool for data collection, labeling, and processing, especially for NLP, because people speak languages. It's a two-sided process with humans on both sides. You submit tasks, and some person perform them, and vice versa. There are so many research directions that I cannot cover all of them, but I believe that if you like Wikipedia-based stuff, you can study the role of both, how to automate the things that are quite boring, and how to spend more useful time for something that deserve it. You can take into account active learning by requiring additional labels from crowdsourcing platform during training your algorithms. Task design is crowdsourcing is a huge area where crowdsourcing is an art, so you can formalize it in some way. There are some quality control issues all the time, and I think it's generally a huge field with a huge perspectives, and I believe it would be a great journey in the future. So that's it. Thank you very much for your attention, and if you have questions, I will be happy to answer.